Okay, so today we are going to start lesson 7.1, which is radical and rational exponents. And if you're following along with your notes, which you're supposed to be doing, you've got a few things on there that I don't have on this slide. The inside's called the radicand, the whole thing's called the radical. What you really need to watch is when you have a radical and you've got a little number right here, that number is called the root or the index, and it has to be included in your answer when you simplify a radical. The root and the power, so this thing's going to be to a power, is what makes up the rational exponent, and it's going to be your base to the power over root. And if you can't remember that, think of it's nice and warm in Puerto Rico. So it's power over root. It's like the one thing in math that's not alphabetical, so I have trouble with that. So anyway, power over root. So what we're going to look at first, and I don't know why this is blue, but you know I did it, so it's probably messed up. We're going to go between exponent form and radical form. So this first one I gave you as an exponent, so I need you to change it to radical form. So you're going to do a radical. The base is the radicand, that's x. The power is the numerator, the root is the denominator. So your root is 6. Now, if you want to put a little 1 here, you're more than welcome to do so, but that's kind of silly. So we aren't going to do that. So now we're going to take this one, y to the negative 9/8. We're going to put a radical. We're going to put y to the negative 9, and we're going to have the power of 8. Oh, wait a minute, Mrs. Evans, we can't do that because y to the negative 9/8 means 1 over y to the 9/8. So if we're going to change that to radical form, it's going to be 1 over your radical, y to the 9th, with an 8 inside the index. Now that should be bothering you. You should be having heebie-jeebies running up and down your spine because you can't leave a radical in the denominator. Those rules don't change till you get to calculus. So we need to rationalize. And when we rationalize with radicals, we're going to talk about it a little bit more throughout this slideshow, but when we rationalize with radicals, we need to multiply by an 8th root over an 8th root. So you're not going to just repeat that actual number inside there. It's not like a square root where if you just write the number twice, you get that number, so it comes out of the radical. We need to multiply by y to a power that's going to be divisible by 8. We already have 9, so we need to get it up to 16. So I'm going to multiply by y to the 7th on the top and the bottom. Now remember, you got to do y to the 7th because that's 1 in disguise, okay? Then what you have on the top, well, that's no good. I don't like that color. What you have on the top is the 8th root of y to the 7th. On the bottom, you have the 8th root of y to the 16. But remember, this is y to the power over root. So 16 over 8 is y to the 2nd. So this becomes the 8th root of y to the 7th over y to the 2nd. Wow, mind blown there, right? That's going to be something that we're going to see a lot throughout this whole lesson. So let's go to the next one. The next one, I gave you 1.5. So 1.5 is not a rational number because it's not written as a fraction. So you're going to rewrite that as x to the 3 over 2. Okay, it's got to be a rational exponent. So when we do that, because it's a rational, that gives us our power over our root. So we go back into radical form. Your base is 8, your power is 3, your root is 2. Now if you look down below, which I don't have here on my screen, but if you've got it on your notes, it says that you cannot have a power greater than the root. So 3 is bigger than 2. So what that really is, you should know this anyway because it's a square root, but we've got a square root. I can make that x squared times x. The square root of x squared is just x, and that leaves me with the square root of x as my final answer. So when you're simplifying, you got to follow those 4 bullet rules at the bottom of your notes also. The next one probably is bothering you. Y'all want to take out an I. Don't do it because that's not what I'm asking you to do here. All I'm asking you to do is go to exponent form. So your base is -10, your power is 1, your root is 2. Now we do know that if we were simplifying it, there would be no real solution, but there would be a complex solution, and you would have I times 10 to the 1/2. Okay? It's getting a little picky for right now, but we're there. This one, we have a 3x cubed underneath. Don't worry about that whole rationalizing thing like we did up there, because all I'm doing is going to exponent form. So I'm taking 3x cubed. The power is 1/2 because it's power over root. So that's 3 to the 1/2 and x to the 3/2. So now we got to practice a little bit of hedging. Now we've already hedged with square roots, but these are going to be different roots. I've got a 5th root, a 3rd root, and a square root. So when I'm hedging with my roots, I'm going to use my prime numbers. So remember your prime numbers, 2, 3, 5, 7, 11, 13, blah, blah, blah. So I'm going to take 288 and I'm going to use 2 because that's the first one I see because it's even. That gives me 144 for a remainder. Remember, I'm stuck with 2 until it stops working. So I'm just going to keep doing 2 until it doesn't work anymore, which is right here. Then I'm going to switch it. I'm going to go to 3. And remember, you got to go all the way down to 1. Now, here's the important part. This thing right here means I need 5 in order to be a perfect 5th root. So if I start counting, I have 1, 2, 3, 4, 5 2s. So that means this is the 5th root of 2 to the 5th times 3 squared. The 5th root of 2 to the 5th is going to just equal 2, and then you have a 5th root of 9 left over. So what I do to cheat is once I circle them, remember we just take out a big 2 and then everything else stays under the root. Guess what you're going to mess up? You're going to forget that index. Don't forget it because it'll be wrong. So now we're going to do 1296. I again see 2 because it's even. You guys might see something else. So I'm going to have 648 divided by 2 is 324. Divided by 2 is 162. Divided by 2 is 81. Switch into 3. 27, 9, 3, take it all the way down to 1. My root tells me how many there have to be. There have to be 3. So there's a group of 3s. That brings out a big 2. Here's a group of 3. That brings out a big 3. So what this is going to reduce to is 6. They all made it out, times the cube root of 3 times 2, which is 6. This 6 right here came from the 2 and the 3 that didn't make it out. If you don't like that whole make it out thing, you got the cube root, that's 2 cubed, 3 cubed, and then you have the 6. So that's where these two came out. When I go to 1575, the first thing I see is 5. And that's going to be 315. Another 5 is going to be 63. 3 is going to be 21. 3 is 7. 7 is 1. This is a good old square root. It's the only one we don't put an index on because it's just kind of a universally accepted thing. I don't know if that's true or not, but it sounded good, didn't it? So I got 25 with the square root is 5. 9, the square root is 3. 5 times 3 is 15. And I still have a square root of 7 left over. Okay, so now what we're going to do is go kind of back and forth sometimes. We're going, oh, look at all those repeated numbers. Whoops. We're going to go sometimes from rational to radical so that we can see what we're doing better. And that's what we're going to do when we have numbers most of the time. So this really means the cube root of 125, which is 5. But if you didn't know that, you can do your little hedging and find out that there's a group of 3 5s. And I don't know why there's 2 2s and 2 3s, but you know, surprise, surprise. The negative here still means 1 over 25 to the 3 halves. So you got some options on this one, but the way I would probably go about this is I would say it's the square root of 25. Now here's one thing I didn't tell you. You can put the power outside. So the square root of 25 is 5, and then I'm going to cube that, and so I'm going to get 1 over 125. You don't have to do the cube first. I don't know what 25 cubed is. 625 times 25, and then I have to figure out the square root. Way too much work. So I always do the root first if I can, and then do the power. So on number 3, we could do it that way, but there is no square root of 11. There is no fourth root of 11. They're not the same radical, so we can't put them together under a radical. But watch this magic. If we take them out of the radical and we go to exponential, I have 11 to the 1/2 times 11 to the 1/4. I've got the same bases here. And on the front page, I've got your exponent rules in case you forgot them. If I have the same base and 2 powers, for example, x squared times x to the 3rd, what do I do with those powers? I add them. So this is 11 to the 1/2 plus 1/4. And when we do that, that's going to be 11 to the 3/4. You can leave it that way, or you can say it's the 4th root of 11 cubed. We're going to just keep doing this. Oh, look at number 4. It's already written the way we want it written. 5 to the 1/2, 5 to the 1/2. The hardest thing is this is the same base. That's 5. And then you have 1/2 plus 1/2. So that's just 5 to the 1st, which is just 5. Here's the common mistake. I'll do it in red. This is the common mistake. Ooh, don't do it. People would take 5 to the 1/2 times 5 to the 1/2, multiply the bases, and then add the powers. Go back in your head to x squared times x to the 3rd. This just says what's being repeated, how many times. So do not make that mistake. 4 to the negative 3.5. I'm going to turn that into 4 to the negative 7/2. The negative tells me I have to go to the bottom. Now you could go to radical form on this, but I'm probably not going to do that. I'm going to multiply by 4 to some power, and I've got to make it become a power that's going to be an integer. It can't be a rational anymore because that's a radical. So I have 7/2. If I add another 1/2, I get 4 to the 8/2, which is 4 to the 4th. Got to do the same thing up on top. That's just 1 times 4 to the 1/2, so that's just 1/2. Now, in all honesty, I'm going to go back to the square root of 4 on that because I probably wouldn't have noticed this before. And oh my gosh, the square root of 4 is 2. 4 to the 4th, I don't know what it is. I don't have a calculator with me. You can figure it out if you want to because it would probably reduce. Wait. I opened up my handy dandy drawer and my calculator's dead. So whatever that is, y'all figure that one out. Well, it's okay. That's bothering me. I can't stop. 4 squared is 16. 16 times 16 is that 256. Yep. So it's 2 over 256, which would reduce to 1 over 128. Okay. On this, we're going to take care of the inside first. Remember your dear Aunt Sally. She says always do your parentheses first. So this is x to the 4th times x to the 7th. When you have a negative power, move it up. So that is x to the 11th to the 1/2. And that just comes out to x to the 11/2. Now, if you leave it that way, that's fine. But if you go to radical form, that's the square root of x to the 11th. Notice the power is bigger than the root. So let's move over here. That's the square root of x to the 10th times x. And why did I choose x to the 10th? Because x to the 10th to the 1/2 is going to simplify. The square root of x is going to stay inside. So I'm going to have x to the 5th times the square root of x. And this is actually the proper answer because that's simplified. So when we look at this one, we've got a lot of stuff going on here. I'm not going to deal with the radicals because I can't do anything with a cube root and a 6th root. So I'm going to change it to rationals. So I have x to the 1/3 over x to the 5/6 power over root. When I'm taking fractions, with the same base, I subtract the exponents. So that's going to be x to the, let's see, times 2, -3 over 6, which would be x to the -1/2, which would be 1 over x to the 1/2, 1 over the square root of x. Got to rationalize it. Since it's a square root, I can just multiply the normal old way, and you get the square root of x over x. The next two problems, we have a problem. The difference between these and the ones that we were doing is I don't have the same base. So what I'm going to do is I'm going to leave 7 to the 1/2 because that's a nice prime number. There's nothing I can do with it. I'm going to rewrite 21 as 7 times 3 to the 1/2. So that gives me 7 to the 1/2 times 7 to the 1/2 times 3 to the 1/2. I'm going to take these two and I'm going to put them together because they're the same base. So that's just 7 because it's 1/2 plus 1/2. Add the powers times 3 to the 1/2. Now that looks a little bit weird, and sometimes you feel like you should do something with that. So when I have this kind of a problem, I leave the 7 outside and put my 3 back under the radical. Same thing's going to happen with 9. So on 9, I've got 3 to the 1/3. 9 is 3 times 3 to the 1/3. So my first one's 3 to the 1/3. On this one, I'm taking the root to, or the power to both of them because there's no plus sign, so I don't have to FOIL or do anything weird like that. And I get 3 to the 1/3 times 3 to the 1/3 times 3 to the 1/3. That's all the same base. So it's 3 to the 1/3 plus 1/3 plus 1/3, which happens to equal 1. So it just comes out to 3. Now I know I'm going kind of fast, but you know what you can do? You can pause and then redo it. Isn't that amazing? If this actually works out, guys, at this point you should be going, wow, Mrs. Evans, you're really good. Did you just say that? You should have. Okay, number 10. Go do that trick again because it's not going to work with radicals. So make it 6 to the 1/4 times 6 to the 1/3. Same base, so I'm going to add the powers. So that comes out to 6 to the 7/12. Because the power is smaller than the root, you could leave it that way, or if it bothers you, you can go the 12th root of 6 to the 7th. I'm not going to find out what 6 to the 7th is. I'm not going to expect you to find out what 6 to the 7th is. We're just going to leave it as 6 to the 7th. So on this one, things get a little bit on the tricky side. We've got 24, square root of 24, and the 5th root of 36. I don't like that because they're not prime numbers. Remember the other one I took down to prime numbers. 24 is 4 times 6. So that's 2 times 2 times 2 times 3. The 5th root of 36, that's 6 times 6. So that's 2 times 2 times 3 times 3. So now I'm going to go to exponents. So I've got 2 to the 1/2, 2 to the 1/2, 2 to the 1/2, 3 to the 1/2. That came from these all being to the power of 1/2. For the next ones, I've got 2 to the 1/5. Ooh, I'm going to run out of space. 2 to the 1/5, 3 to the 1/5, 3 to the 1/5. And that came from all of this radicand being taken to the 1/5 power. So then I'm going to put it all together. I'm going to move over here because I ran out of space. I've got 2 to the 1/2, 1/2, 1/2. So that's 1/2 plus 1/2 plus 1/2. Some of us could say 3 times 1/2. 1/5, 1/5. So plus 1/5 plus 1/5 times 3 to the 1/2 plus 1/5, 1/5. So that's going to be 2. This would be good if I'd done this ahead of time, wouldn't it? So these are all going to be over 10. Let me do a little cheating over here. They're all going to be over 10. So that's going to be 5, 5, 5, 2, 2. So 5, 10, 15, 19 tenths. Times 3, these are all going to be over 10. So that's going to be 5 plus 2 to the 9 tenths. So on the 2, I've got a power bigger than the root. So what I'm going to do with that one is make it 2 to the 10 tenths plus 9 tenths. The 3 I'm just going to leave as 9 tenths. So what I'm going to do with that, the 2 to the 10 tenths is just 2. That comes outside. And then I have the 10th root of 3 to the 9th. Whoops, that's supposed to be a 2. 2 to the 9th times 3 to the 9th. And you could figure out what those are, but again, you don't need to for me. Or could you? Could you do this? Since they're both the same power, you could say 2 times 3 to the 9th. So it would be 2 times the 10th root of 6 to the 9th. That 9 doesn't look very little, does it? Make a little 9. Okay, there we go. Oh, I like that better. Happy face. All right, so number 12, it looks like we cannot do this because they have different roots. But remember, you can go from radical form to exponent form. You'd have a rational exponent of 1/6 and 1/3. And then when we have the same base, so that's the important thing here, is they have the same base. That means we can do it. Happy, happy, joy, joy. We subtract the exponents. So it's 1/6 minus 1/3. When I do my little TP, I get 3 minus 6 over 18. So it's 4 to the negative 3 over 18, which is 4 to the negative 1/6. Now you might think you can stop there, but you cannot because we have a negative exponent. So it's 1 over 4 to the 1/6. Now remember, that's the same as the 6 root of 4. So you got a radical in your denominator, can't do it. So let's go back to 1 over 4 to the 1/6. We're going to rationalize that by multiplying by 4 to the 5/6 over 4 to the 5/6. So we have 4 to the 5/6 over 1/6 and 5/6 is 6/6, which is just 1. So this is a good answer. Or you can say it's the 6th root of 4 to the 5th over 4. This is actually a better answer. So on number 13, it's actually kind of a just simplify it thing. You got to just remember that means the cube root of 8 squared, or it also means the cube root of 8 squared. If I do this first one, it's the cube root of 8 squared, which is the cube root of 64. Then I go over here to 64 and I hedge it. And all you can hear is click, 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 click from my pen. So I'm looking for groups of 3. So there's a group of 3, bring out a 2. There's a group of 3, bring out a 2. 2 times 2 is 4. If I do the square root, or the cube root of 8 squared, well, the cube root of 8 you should know is 2. If not, it's right here. Squared, and I get 4. So either way, I get 4. Very exciting stuff. Okay, number 14, I got a power to a power. So I'm going to start out by saying x to the negative 4/3, because power to power, remember, you multiply. So that's 1 over x to the 4/3, which is, I'm just looking at my notes and I don't even know where I have these problems. I feel like I'm making them up. Which is something I need to rationalize. So I need to multiply by x to some power. Now remember, I'm going to add that power and this power, and they have to equal a nice integer. So if I take 1 more third, that only gives me 5/3. But if I take 2/3, that gives me x to the 6/3, which is going to become x to the 2nd. Now here's my problem with this part right here. This, put it in black because it's a problem. Ooh, problem. My instinct is to subtract because they're the same base. But what that's going to do is that's going to get me back to here, back to here, back to here, and I've got no good. So don't do that. just leave it as the cube root of x squared. Remember, I can't take care of the x squared and x squared because one's under a radical and one is not. Okay, my math program is kind of hard to read, but that's x to the 1/2, y to the -2/6. So the first thing I'm going to do is take care of this power, no plus sign, so I'm just going to take x to the 1/2 to the 6th and y to the -2/3 to the 6th. That's going to be x to the 3rd, y to the -4th. So all I really have to do on this one is x to the 3rd over y to the 4th. Whew, no radicals involved, nothing sneaky, no simplifying. Life is good. 3.5, remember we can't have decimals. We have to turn it into a rational number. So it's 64 to the 7/2. Oh my gosh, 64. I'm going to put it underneath the square root because that's my root, and take that whole thing to the 7th. Square root of 64 is 8. Take it to the 7th, and if you want to multiply that out, you go ahead. 8 to the 7th would be an accepted answer. 17 is a mess, but I'm going to take care of these first because I have negative powers and I don't like it. So I'm going to do x to the 2/3. I'm going to move that y to the 1/4 down. That takes care of the numerator. In the bottom, I have x to the 1/2, and I'm going to move that y to the 1/2 up. So remember, negative powers move to the other part, top to bottom, bottom to top. So now I have x to the 2/3 minus 1/2, and I have y to the 1/2 minus 1/4. So that's x. 2/3 minus 1/2 is going to be 1/6. Y is going to be 1/4, 2/4, 1/4, 1/4. Is that right? 4 minus 2 is 2 over 8. Yeah, 1/4. Now, you could leave it that way if they say in radical form. Oh, only if I can embrace my inner Stella. What would we have to do? We can't put them under their own little radicals. I would put them both to the power of 12. 1/6 is going to be 2/12. 1/4 is going to be 3/12. So in radical form, I'd have to go to the 12th root of x squared y cubed. If they do not say that, that's an acceptable answer. But there are going to be times in your life when you're going to need that answer in your future mathematical career. Okay, this is my last slide, last two examples. This one a little faster than I thought it was going to go, so yay, yay, yay. You're going to have homework time. Little editorializing here. Don't forget, your FUR4 is due on Monday. So, absolutely nothing reduces inside, does it? So I'm going to take 8 to the 1/3, x to the 6th to the 1/3, 27 to the 1/3, and y to the 9th to the 1/3. Now, if you don't recognize 8 to the 1/3, it's the cube root of 8. Hopefully you recognize that. On the x, you're going to take it, so let's put that in parentheses because that's how I like it. We're going to multiply these two, so that's x squared. If you don't recognize 27 to the 1/3, make it the cube root of 27. Hopefully you recognize that. And it's going to be y to the 3rd. So the cube root of 8 is 2, x squared. Cube root of 27 is 3, y cubed. Nothing I can do with that. We're good, good, good. X to the 1.4. X to the 1.4, 1.4, that's 1 4/10, which is otherwise known as 1 2/5. I'm saying this quietly because this is what's going on in your head, which is 7/5. So that's x to the 7/5. Can't leave it that way because your power is bigger than your root. So if we put that under the 5th root of x to the 7th, we need to see if we can take anything out. When the power is bigger than the root, we can. So that's x to the 5 plus 2. So that's the 5th root of x to the 5th times x to the 2nd. I don't really know what I was doing there, but I'd already written it down. I'm a crazy lady. So that's going to come out as x to the 5th root of x squared. I just thought of another one. I don't have another slide prepared, and I don't know how to add it during this part of the program here. So I'm just going to say, what would you do if you had x to the 1/4? I don't think that's what I want now that I'm thinking about it. X to the 1/4. Let's just say, forget that. Let's just say it came out to the 4th root of x squared. Could you leave it that way? Okay, you cannot leave it that way. Look at all these asterisks. I like those today. You would have to make that as x to the 2/4, which is x to the 1/2. So it really reduces to the square root of x. So what you can do is when you're looking at your power and your root, or your power and your index, you're going to say, can they both be divided? Divide that by 2, you get 1. Divide that by 2, you get 2, and you can go right there. But you can only do that if you had, wish I knew how to make this bigger. If you had the 4th root of x squared, let's not make that the 4th root, let's make it the 6th root of x squared y to the 3rd. If you want to keep it all under the same radical, there's nothing you can do, because that is x to the 2/6, y to the 3/6. So that would be x to the 1/3, y to the 1/2, and they would have different roots, so you couldn't put them back together. But if it's only one thing, or if they all divide out and keep the same root, you can simplify it. But if not, keep it as the one radical. Okay? That's all I got for you today. You're going to go and you're going to do your homework. It's on OneNote, and the sub has some paper copies if you want paper copies. Thank you for playing along with This is Rational Exponents and Radicals 7.1.